this is the problem I left you with at the end of the last video. We have this formula, which shows up in chemistry, and we were trying to solve it for k. So k shows up inside the argument of the log here. What's kind of nice is that log is already isolated, so I don't need to do any work to get it by itself. We're ready to just undo it. So I can rewrite this in exponential form. This is saying the exponent I need when e is my base to get k over a as a result. That exponent is negative e over rt. Do make sure that that's a capital E. That is not the same as this number e in the base. Okay. All right. I always think of this as just sort of rearranging this in exponential form. Notice this is equivalent to just raising both sides, taking e and raising it to both sides. If I were to take e to the natural log of k over a, the exponential function and the log would undo each other and I'd get k over a, and then on the other side I'd get e to the negative e over rt. Okay, so there are two ways you can think about that step. Now if I wanted to solve for k, I would just multiply by a. So a e to the negative e over rt is equal to k. Excellent. So that's just rearranging an equation that's given to solve for a particular variable. Another thing we'll see in this section is that sometimes we'll have sort of a generic model that describes a general situation that we can make more specific to match a particular situation. An example would be anytime I have a population that's growing at an exponential rate. I would have an equation that looks something like this. P equals P naught e to the kt. Okay. Now, that equation would be given to you in the homework, but that's, it would basically be saying come up with an equation of this form. So this form would be given, but that's all that would be given. So you'd need to understand what it meant and how to adjust it. So let's explain that. Okay. So I basically have four letters here. I've got P and T and P naught and K. I suppose you could argue that E is a letter, but that's actually E, the number. Okay. Now, only two of these are honest to goodness variables. P is standing for my population, and that's going to be my output variable. That's what we call the dependent variable. It depends on T, which is time, and that's our input variable, also called our independent variable. So that's my input, and that's my output. These other letters, P naught, anytime you see a variable with a subscript of 0, that almost always is going to mean that it's that thing evaluated at time 0. So P naught is the initial population, which would simply be the population at time 0. Time 0 generally does not refer back to whenever the Big Bang happened, doesn't even refer back to when people first appeared on the Earth. Okay? Time 0 is going to be our starting time. So we're going to pick a time that's our starting time, and we'll call that time 0, and we'll measure things from there in whatever units we want. I'm going to actually be using years for this particular example. Okay. And then K would be what we call our growth rate coefficient. And that's just going to be a number that's going to be telling us monitoring how quickly the population is growing. Okay. If this is population growth, K will be a positive number. If I had something that was decaying, then I would have a negative number up here. Because I know my base E is bigger than 1. So if I take E to a positive multiple of T, I'm going to be getting exponential growth. If I took E to a negative multiple of T, E to the negative T is the same as E to the negative 1 to the T would be the same as 1 over E to the T. That's a number that's between 0 and 1. That would give me exponential decay. So if I'm talking population growth, I'm going to expect that that K will end up being a positive number. Okay. Now, P naught and K are not variables for any one particular population. They're variables in the sense that this model applies to lots of different populations. And so if I'm talking about the population of people in Mission Viejo, that's going to have a different P0 value than if I'm talking about the population of hedgehogs in Nanuet, New York, which is where my mom lives and she likes hedgehogs. Okay, there would be a different initial population for those two different populations. Okay, and presumably they would be growing at a different rate. There's no reason for me to think that people in Mission Viejo are reproducing at the same rate as hedgehogs in Nanuet. Okay, so I would probably have a different number here. For any one scenario, these are constant, but I write them here as variables because this is the generic one. What I want to do is try to make it more specific. So let's suppose that we're going to be measuring population in a certain city, and let's let P be in millions of people. So 3 wouldn't mean that the city had 3 people in it. It would mean there were 3 million people in it. Okay. Let's measure time in years. And let's measure it in years from 2010. So basically what I'm doing there is I'm saying, okay, time 0, that's going to be January 1st, 2010. The beginning of 2010, that's what I'm going to call time 0. So if T is 5, 5 years have passed. So that would be the beginning of 2015 instead. Okay, excellent. And let's suppose we know the following bits of information about this particular town. In a given year, I know the given population. So let's say we know what it is in 2010. Okay. And in 2010, it was 5. Now, not 5 people, 5 million people. Okay. And let's suppose by 2020, that city had grown to be 7.2 million people. Okay, so with this data, I should be able to replace P0 and K in my model with specific numbers. Okay, so I start with the generic model. P is equal to P0 times e to the kt. Now I might be able to just see P0 is 5, okay, because that's going to correspond to time 0. If I didn't see that, I can say this corresponds to an ordered pair. The year 2010 corresponds to when time is 0. So the year 2020 will correspond to when time is 10. If I can say the population is 5 when the time is 0. Now when I plug that in, notice this just becomes 5 equals P0 e to the 0, but e to the 0 is 1, so 5 is equal to P0. Again, I think it's simpler to realize, hey, if that's where we are when time is 0, that symbol means the initial population, so that's just going to be 5. Okay, so I can now make my model a little bit more specific. We're halfway there. I can replace P0 with 5. So now I need to figure out what K is. I'm going to get that by plugging in what corresponds to my other piece of data. The second point, the population is 7.2, meaning 7.2 million people, in 2020, which is when time is 10. So that would be 5e to the 10k. I still don't know what k is, but I'm plugging in 10 for t. Okay. So I can divide both sides by 5. So we've got e to the 10k is equal to 7.2 divided by 5. Okay. I'm going to go ahead and simplify that just because that division problem actually does work out nicely. 7.2 divided by 5, it's going to go in once, 4 times, 4 times. So that's just 1.44. Okay. So that was a relatively quick one to simplify. If you've got something really messy, I would be fine with you keeping it that way. Okay. So right now we've got e to the 10k is 1.44. Okay. I'm going to now take the natural log of both sides. So the natural log of e to the 10k is the natural log of 1.44. And so 10k is the natural log of 1.44. Yes, I'm sorry. Because the natural log of the exponential function undo each other. So to get k, I would divide by 10. So it's the natural log of 1.44, all divided by 10. Not dividing 1.44 by 10, I'm dividing its log by 10. Okay, excellent. So now I can say that my model is P is equal to 5 times e to the natural log of 1.44 over 10 times t. So I've plugged in specific numbers for P naught and for K. This would be how you would do this on exams when you don't have access to a calculator. In the book, they're often going to have you just plug that in and round things. Let's see. The natural log of 1.44 divided by 10. K is about 0.0364, blah, blah, blah. Let's just say about 0.036. Okay. If on take-home work I wanted you to round, I would tell you a specific place. I would just leave it like that. Okay. Now, if you were asked to find an equation of this form, you would leave it in this particular form. I just want to show you, if I had the freedom to change the form a little bit, there is a simpler way I could write this. Because notice, this is 5 e to the, I'm just going to rewrite that exponent as the natural log of 1.44 times t over 10. That's exactly the same. I've got a natural log of 1.44, a 10 in the denominator, and a t. But then I could say that's 5 times e to the natural log of 1.44 to the t over 10. And this is just 1.44. So I could say, I'm running out of space. I could say my population is 5 times 1.44 to the t over 10. I think that's actually a little bit nicer, but do make sure that you read the directions. If you're asked to have something in this form, keep it in this form with a base of e. But that's a way that I can simplify a sort of messy number in the exponent by just using a different base.